Welcome back. We're going to move on to a new topic now, and that's the topic of cosets. What the general idea with these things is it provides us a means of splitting a group up into pieces based on a particular subgroup of a group. So the idea is we take a subgroup of our group, and we use this to essentially break our group up into a number of disjoint pieces all related to this subgroup. And the conceptual tool that we use to do this is that of a coset. Now there's not a huge amount of point in talking too much about this in the abstract like this, so we're going to dive straight in, define these things, and start working with them to get a feel for how they work. So we'll begin with a bit of notation. So we're going to take a group G and a subgroup H of that group. And then we're going to take a specific element A of our group, and then we're going to define A times the subgroup. It's kind of like a member of the group times the subgroup H itself, just to be the set of A times little h, where you take H ranging over the entire subgroup capital H. Collect all those things together and we have a set which we call A capital H. And we can likewise multiply A on the right instead of on the left, and we get the corresponding set HA if we do it this way around. Okay, so that lets us define these cosets as follows. So these sets AH and HA, they have special names. AH is called the left coset of H in G containing A. So notice it's a coset of H. It's a set that's related to H, so maybe think of it as a set corresponding to H if you like, coset. So AH is the left coset of H in G containing A because it's multiplied by A on the left. And HA is the right coset of H in G, also containing A. Okay, so this A also has a special name. A is called the coset representative of AH. Sometimes called the coset leader. Of AH, or HA if you like. Okay, and just like with our groups, we use the absolute value notation to determine the number of things in it. AH equals number of elements in AH, and similarly, HA is the number of elements in HA. Alright, so that's the definition of a coset. We take a subgroup first, then we choose an element A of our group, we multiply everything in the subgroup by that A, and the resulting set is called a coset of H. So best thing to do at this point in time is to jump straight to an example and see how that works in practice with a group we know. So if we're going to use, for example, we're going to use the symmetric group S3. Right, so here it is. We want to find all the cosets of, here is a subgroup of S3, the one containing the identity and 1, 3, a transposition. We want to find all the cosets of this subgroup in S3. Now let's just remember what S3 was. Remember S3, the elements are, there are 6 of them. They were 1, 1, 2, 3. If we write them in cycle form, 1, 3, 2. And then there are the 3 transpositions, 1, 2, 1, 3, and 2, 3. So we should be able to form potentially 6 cosets here. If we take one element out of S3 and multiply it by H, which is our subgroup, let's just call that H, then we should be able to build our various subgroups. So what we're going to do is we're going to start at the beginning and write down what each of these things are. So first off, the identity times H, that means I just take everything in H, so at each point in time we should be looking at this set here, and I multiply it by the identity. Quite clearly that's just going to give me H itself, right? So that will just be equal to H. Okay, let's take a step up. Now we'll do 1, 2, 3 times H. So the way I interpret this is I take my 2 elements of H and I multiply them each by 1, 2, 3. So 1, 2, 3 times 1, that gives me just times the identity, just gives me 1, 2, 3. And then 1, 2, 3 times the transposition 1, 3 gives me 2, 3. I encourage you to check these for yourselves. So there we have what the coset 1, 2, 3 times H looks like. And I guess I should be saying find all the left cosets here. All right, I can continue on. So next up is going to be 1, 3, 2. So let's have a go at that one. 132 times h obviously, every time the first element is going to be just the element itself because it's times that entity. 132 times 13 happens to be 12. Again, I encourage you to check this for yourself. And that's what that is. Okay, so far we've built 3 different cosets. And let's just keep on going and see what happens next. So 12 times h. That will give me 12. Great. And then the second one is going to be 1, 3, 2. Okay, something odd has happened here. That looks very much like the one we just did. That is also the same set as 132 times h. So here's our first example of a coset. We took a different element times h and we got the same coset back again as we had already seen. We can do it again. So now we go for 1, 3 times h. Again, the first element is going to be 1, 3. You can possibly even guess what I'm going to get here. 1, 3 times 1, 3 is just the identity because transpositions are their own inverses. And so that just gives me h back. And the last one, 2, 3 times h, gives me 2, 3 and 1, 2, 3. And I've already seen this one before as well. That's the same as 1, 2, 3 times h. Alright, so we have our 6 cosets, but actually only 3 of them are unique, or distinct, sorry. So if we put maybe we'll put a little asterisk by them. So let's just make a little note of that. We got 3 distinct cosets of 2 elements each. And one thing else that's worth noting is there's no crossover between any of those cosets. So just put that little piece of information in your head for now, and we'll revisit it again as we look at some more examples. So our next example is going to be in D4, and again we'll take a 2-element subgroup. We'll take the center, and we'll find the cosets of that in D4. Right, so here it is. So the center of D4 is a subgroup is R0 and R180. And let's go through exactly the same way as we did with the previous example and find all of the cosets. So we'll just go through each element of D4 and figure out what the coset is and if we've already seen it. So we're kind of keeping an eye out for the unique ones. So first off, multiplying by the identity, we just get the same thing back. So I'm not going to spend any time on that one. R90 times K, you can see we'll quite clearly get R90 times R0 is R90. And R90 times R180 is R270. And then we do R180 times K, and I get back to K quite quickly. I'll get R180, and then R180 times R180 is R0. So actually, I get my subgroup K back again. If I do R270 times K, I will get R270, and if I multiply it by R180, I will get R90. And there is one we've seen before. That is the same as R90 times K. Maybe you can see where this is going. If I now do V, I'll have to do H first, H times K. That gives me H and V. And then V times K gives me V and then H, which is the same as HK. So again, if we were going through asterisking our unique ones, is that one. There's that one. In fact, let's put them here. That one doesn't appear more than once, or that one's unique. R180K, we've seen that already, that was R0. R270K, that was the same as R90K. HK, that was a new one, so HK, that gives us H and V. VK gave us that one back again. Do the same thing with the diagonal, so DK reflections, and we'll get D times R0 gives us D, obviously. And then we get D prime when we multiply R180. And finally, D prime times K, again, consulting the Cayley table or figuring it out by hand, gives me D prime D, which equals DK. So this time, if we look at, there are 4 distinct cosets this time. Of 2 elements each again. So each time the number of elements in the coset appears to be the same as the number of elements in the subgroup, and it seems to be splitting our group up into a number of distinct sets. I don't know what's happened there. Let's try that again. Okay, into a number of distinct sets that don't overlap. So again, if you look at the 4 cosets that I've identified as being unique, there's no crossover between any of them and any other one. So DK and HK do not overlap at all, neither do any of them. So one of the things that we're beginning to observe here is that cosets actually partition or create a partition of our group. Okay, they divide it up into distinct pieces, and that's a really useful thing to be able to do because it enables us to say something about the sizes of subgroups and things inside the group. But we'll continue on with a couple more examples, or maybe one more. This time we'll look at a subgroup of Z9. So let's take, I'll take 036 being a subgroup of Z9. So let's just look at the cosets this time. I have 0 plus H. Remember, we're dealing with a group with additive notation now, so we got to use plus instead of times. So that's what that looks like. 0 plus H, I just add 0 onto each of the numbers there. Just gives me the set 036. And that just obviously gives me my set H. And it turns out that also equals 3 plus H and 6 plus H. And then I have 1 plus H is going to be 1, 4, and 7. And that, you can check this yourselves, is the same as 4 plus H, which is the same as 7 plus H. And finally, we've got 2 plus H, which is the set 2, 5, and 8. That is the same also, you can check this, as 5 plus H, which is the same in turn as 8 plus H. So this time we have 3 cosets of 3 elements. So again, it's divided my group up into 3 pieces of equal size, and again, look at the 3 cosets. There is no overlap between the elements in any of these, and so it's provided us with a partition of our group into pieces. Okay, now other things that are worth sort of observing here. Notice the 3 elements that gave us the same coset. For example, that last one there, 2, 5, and 8. If you look at the elements in the coset themselves, they are all members of that coset, 2, 5, 8. And if you go back over all our other examples, let's just take another one here. Let's take V times K is the same as H times K, and they make the coset V and H. And likewise, if we go back to one of these ones, 1, 2, and H, 1, 3, 2, and H, the coset, surprise, surprise, is the coset containing 1, 2, and 1, 3, 2. Alright, so what we can do now is we can sort of take all of these observations that we're beginning to make, and we'll summarize them as a big long lemma that comes from Gallian that I'll refer you to the proofs for, that lists properties of cosets that we've kind of been seeing as we've been working through these examples, but it puts them all together in a nice way. So let's build this up bit by bit. The first property of cosets in our lemma is that A is a member of AH, and you can see this because the identity is a member of H, and A times the identity is quite clearly going to be a member of that coset. Okay, our second property is one saying that AH is equal to H if and only if A is a member of H itself. Okay, so I get to my subgroup H by making a coset of it, A times H, only if A is a member of that subgroup to start with. Otherwise, I get a different set altogether, and it's not my subgroup. Okay, the third one is to do with the coset multipliers, or the numbers out the front of the coset. Simply says I can form the set, if I want to do AB times H, then I can form the set BH first, the coset BH first, and then multiply everything by A, and I'll get the same result. And similarly for the right cosets as well. Okay, the next one is when are 2 cosets the same? and we have AH is equal to BH, i.e. these two cosets AH and BH are the same thing if and only if one of them, A, is a member of the other one, BH. Okay, which leads us to a very similar one, even though it maybe looks a little different. Either AH is equal to BH, or they are disjoint altogether. And the way we can write that is AH intersection BH is the empty set. That's how we write the empty set phi. Okay, again, I'm not going to prove it. I'll refer you to Galleon for all of these proofs. None of them are in and of themselves all that difficult, but it's kind of collecting together these observations that we made with all of our examples. This one is a similar one that says AH equals BH if and only if, this time, A inverse B is a member of the subgroup H. It's an equivalent statement to our earlier one. Let's just tidy up that arrow. Okay, so two more. This one says that the size of any two cosets are the same. Okay, so notice all of our cosets came out to be the same size. This is something we can actually prove. The size of AH is equal to the size of BH automatically. All right, now one that relates left and right. AH equals HA if and only if H is equal to AHA inverse. That means we take H, we multiply everything on the left by A and on the right by A inverse, and then we get our set AHA inverse there. Okay, that one's less important perhaps. Finally, AH is a subgroup of G. So notice cosets in general are not subgroups, only H itself is a subgroup. So AH is a subgroup of G if and only if A is a member of the subgroup. In which case AH would just be H by our property number 2, and then AH would therefore be H and therefore a subgroup of G. So the only coset that is a subgroup of the group is the actual subgroup itself. None of the other cosets are actually subgroups. Okay, so if we take some of these properties together, number 1 says that every element is a member of its own coset. So that's the one where we looked at our examples and we saw that, for example, 2 plus 036 and 5 plus 036 and 8 plus 036 all were in the same one. That one, together with the fact that cosets are disjoint, together with the fact that coset sizes are equal, those three taken together imply that we get the partition that I've been talking about. So 1, 5, and 7 imply that the cosets partition the group into equal size subsets. Okay, so again, we'll do one more example, and just to finish off with, and we'll find the cosets of, this time we'll look in one of our U groups, we'll look at the coset of 1, 15 in U of 32. Okay, so that is a subgroup. 15 times 15 is 225, which is quite close to the right kind of thing. So let's figure that out. 1H, we're going to go through them all, is equal to H, which just equals 115. Now what we should find is that these partition U of 32 into a number of equal pieces. 3H, that's going to be 3 times 1, and 3 15s are 45, which sounds a lot like 13, more than 32. 5H is going to be 5. 5 15s, that's 75, which sounds like 11 more than 64. We keep on going. 7H. These are all relatively prime to 32. 7H is going to be 7, 9. Now the next thing in U of 32 is 9, but we've already seen 9, so that should be equal to 9H. So there's no point in making 9H because we know that we'll get 7, 9 again. Next thing relatively prime to 32 is 11. 11 is also already been seen. We've got 11 in this one. We then have 13 in this one, 15 in this one. So the next unique subgroup we'd expect to see is 17H. So 17H is going to be 17. 17 15s is something or other, which if you have prepared in advance would give you 31 here, mod 32. Next up is 19H. We haven't seen 19 yet, so that's going to give me 19. And again, you can check the calculations yourselves. 29. 21, have we seen that yet? No, we have not. 21H is going to be 21 and 27. And finally, 23H is going to give me 23 and 25. Okay, remembering that all the things relatively prime to 32 are just the odd numbers, because 32 only has factors of 2, or factors of powers of 2. So the next thing up will be 25. We've got that one here. 27, we've got that there. 29, we've got that there. And 31, we've got that there. So that covers off all of the elements of U of 32, of which there are 16, these odd numbers. And there is our partition of those 16 numbers, 1 through to 29, into 8 sets of 2 elements each that do not overlap. So that's really nice. It means that we always get this partition using our subgroups. And the other interesting fact about what we're doing here is that it means that the size of the subgroup must be a divisor of the size of the group. This is a theorem that we stated for cyclic groups already, but we haven't stated it to be true in general. And the idea of cosets kind of leads quite naturally to this, and it will be the subject of our next video, that automatically, because of these ideas about cosets and partitioning, the size of the subgroup has to be a factor of the size of the group. Otherwise, you couldn't partition evenly. It wouldn't make any sense. So that's the topic for the next video. We will catch you then. Until then.